The signal repeats every 17 minutes. And the deeper scientists drill into the ice, the stronger it becomes. But when they finally uncover what's beneath the surface, the entire research team wants the discovery buried forever. It's 3:12 a.m. when the anomaly appears. You re-14 hours into a 36-hour data shift at Halley 6 research station, and the only thing keeping you awake is a cold cup of instant coffee and the monotony of seismic waveforms scrolling across your monitor. Outside, the wind is doing what Antarctic wind always does, screaming at the walls like it has a personal grudge. The bass groans. The lights flicker once, then hold. Your name is Dr. Maravas, glaciological seismologist, 31 years old. You've been stationed here for 11 months, part of a joint ESA-NSF deep ice monitoring project. Your job is to watch for subglacial shifts, tectonic microevents, meltwater drainage patterns, the slow mechanical grief of a continent losing itself from underneath. You are good at this job. Methodical, patient. You have spent almost a year learning to read ice the way a cardiologist reads a rhythm strip, looking for the thing that doesn't belong. Tonight, something doesn't belong. The waveform appears at 3:14 a.m., nested inside routine background noise like a word hidden in static. Your first instinct is instrumentation error. You've seen that before, a loose coupling on a geophone array, a temperature differential warping a signal chain. You run the diagnostic. Everything checks out. The array is functioning perfectly. The signal is real. You sit forward. The coffee goes cold and forgotten. What you're looking at isn't seismic in any conventional sense. It isn't tectonic. It doesn't match any meltwater acoustic signature in your reference library, and that library contains over 40,000 tagged samples. The waveform is structured, repeating, not random. You pull up the raw data and run a frequency analysis. The signal is sitting at 0.23 Hz, well below human hearing in the infrasound range, pulsing at intervals of exactly 47 seconds. Not approximately, not roughly, exactly 47 seconds to the millisecond for as far back as the archive data goes. Your hands are steady when you start typing the retrieval query. You don't know yet that they won't be steady for very much longer. The archive goes back 9 months, which is when your monitoring array reached full operational depth. Sensors bored into the ice shelf at varying depths between 800 and 2,400 meters. You pull every dataset from every array. The signal is there in all of them. It has been there since the sensors went in. 9 months of a perfectly repeating, non-seismic, structured acoustic signal emanating from approximately 3,100 meters below the ice surface, which puts it somewhere inside or just above the continental bedrock. You know what's down there officially? Old ice. And beneath that, rock that hasn't seen sunlight since before complex life existed on this planet. You stare at the screen for a long time. You know what you're supposed to do. You're supposed to log the anomaly, flag it for review, and send it up the chain to your project lead, Dr. Fenwick, who will be awake in 4 hours. That's protocol. That's the safe, professional, appropriate response to an unexplained data event. You've done it before with lesser anomalies. It's not exciting, but it's correct. You start writing the flag report. You get 3 sentences in before you stop. Because here is what you already know and are not yet allowing yourself to fully think. A structured, repeating signal at a mathematically precise interval is not a geological event. Geology doesn't do intervals. Geology doesn't do precision. What geology does is chaos, beautiful patterned chaos, but chaos nonetheless. Pressure and heat and time do not produce a 47-second pulse. You close the half-written report and open a new analysis window instead. This is the first decision. It seems small. It doesn't feel small. By 6 a.m. you have a cleaner picture, and the picture is worse than the original anomaly. The signal isn't just precise in its timing. It has harmonic structure, overtones at specific mathematical ratios above the base frequency. You run it through a Fourier transform and the output makes you stand up and walk to the small porthole and look out at the gray Antarctic dawn for 30 seconds before you trust yourself to sit back down. The harmonics are arranged in a ratio sequence. You recognize it. It isn't obscure. It is one of the most recognizable mathematical progressions in the physical sciences. A sequence that appears in orbital mechanics, in the resonance relationships between planetary bodies, in the vibrational modes of molecular structures. It appears throughout nature because it is a property of space and matter themselves. But it shouldn't be here like this, coming out of bedrock, pulsed through 3 kilometers of ice. Your coffee has been cold for hours. You don't notice. You open a second monitor and start pulling geological surveys of this region. You're looking for any natural structure, a cavity, a resonant chamber, a trapped gas pocket that could theoretically produce harmonic acoustic output. You find nothing. The surveys show uniform subglacial geology for this sector. Dense, ancient basalt. No cavities. No anomalies. Nothing that would sing. At 7:23 a.m., Dr. Fenwick walks in with his own coffee and stops when he sees your face. "What happened?" he says. You show him. The next 6 hours are the longest of your professional life. Fenwick is a careful man. 30 years in the field, the kind of scientist who treats extraordinary claims like they are personally trying to rob him. He goes through your analysis 3 times independently. He pulls in the station's 2 other researchers, Nakamura from the atmospheric team and Dr. Reyes, the ice dynamics specialist. Neither of them is in your field. It doesn't matter. What's on the screen is not ambiguous. Nobody says the obvious thing out loud for the first 2 hours. You are the one who finally says it. This is artificial. Fenwick doesn't argue. That's when you know the situation has changed completely. If Fenwick doesn't argue, there is no argument left to be had. The protocol for an anomalous discovery of potential significance to the broader scientific community is to report upward through the project's institutional hierarchy, which means NSF in the United States, ESA in Europe, and by treaty obligation, the Antarctic Treaty Secretariat in Buenos Aires. You are required to report it within 24 hours of confirmation. Fenwick begins drafting the communication at 1:15 p.m. You watch him type. You are thinking about what happens next, and none of the options feel comfortable. You already know that once this goes up the chain, it leaves your hands. That is also protocol, and it is also, you suspect, the end of your direct involvement. Projects like this, if this becomes a project, don't stay with field researchers. They move to larger institutions, larger teams, people with different classifications and different mandates. The station and its equipment will still be here, but the thing driving it will no longer be yours. You think about this for a moment. Then you ask Fenwick to let you review the report before he sends it. He looks at you. Of course, he says. What he sends is accurate and complete. You don't change anything. But reading it, you understand for the first time that you are now holding something that cannot be held, that the moment you confirmed the signal was real, the signal stopped being yours alone to know about. The report goes at 2 p.m. By 4:30 p.m., NSF has acknowledged receipt and flagged it for priority review. By 8 p.m., you have a satellite call with a man from NSF's Office of Polar Programs whose title you don't catch and whose tone is very controlled. He asks you 4 specific questions about the signal's characteristics, listens to your answers without taking audible notes, and then thanks you and ends the call. That night, you don't sleep. You lie in your bunk and listen to the wind and think about the 47-second pulse continuing down there in the dark, unchanged, indifferent to whether anyone is listening. The next 10 days are a specific kind of purgatory. You continue your regular monitoring work. You file your standard reports. You eat in the small cafeteria, you run on the indoor track, you exchange the brief, cautious conversations that people exchange when everyone in a small space knows something significant is happening and no one is authorized to discuss it openly. 3 separate encrypted communications arrive for Fenwick. He tells you only that review is ongoing and that additional expertise is being assembled. He says this the same way someone says the weather is expected to change. Technically informative, practically meaningless. On day 8, you go back to the signal data on your own time. You aren't supposed to be actively investigating. The flag protocol effectively puts the anomaly under institutional review, which means primary analysis should wait for the assigned team. You know this. You do it anyway. Not because you're reckless, but because you have been sitting 3 kilometers above something that shouldn't exist for 9 months without knowing it. And now that you know, patience has become physically impossible. What you find on day 8 changes the shape of what you understand. The signal is not static. You missed it the first time because you were looking at a 6-day sample. When you pull the full 9-month archive and run a long baseline comparison, a pattern emerges. The signal's amplitude, its strength, its loudness in acoustic terms, has been increasing. Slowly, incrementally, less than 0.5% per week. Over 9 months, it has grown by approximately 17%. Something down there is getting louder. You write this up and send it directly to Fenwick at 11:40 p.m. He reads it within minutes. You can see the receipt timestamp. He doesn't reply that night. On day 11, a twin otter arrives with 4 people you haven't met. They introduce themselves with first names only and institutional affiliations that are real but vague, one from Caltech, one from a UK signals intelligence consultancy that you've never heard of, one whose affiliation he gives as DARPA adjacent, which I know sounds worse than it is, and one woman who says only that she's with an interagency working group and lets that sit there unchallenged. Her name is Dr. Sharon Coletti. She is the one who talks to you the most. She asks you to walk her through your original analysis from the beginning. You do. She listens the way very few people listen, without preparing her next question while you're still talking, without performing engagement. She asks follow-ups that are precise and technically sophisticated, and you realize quickly that she already understands the data. She isn't learning from your walkthrough. She is evaluating you. Why did you go back to the archive on day 8? She asks. Because the signal is changing, you say. And a changing signal is different from a static one. In what way? A static signal could theoretically be a natural phenomenon we don't understand yet. Something geologically novel. A changing signal, one that's growing in amplitude over time, implies a process. Something is driving it. Something is generating it and increasing output. She looks at you for a moment. And what do you think that something is? You have been very careful for 11 days not to say out loud what you think. You have confined yourself to data descriptions and technical characterizations and the passive, hedged language of careful science. You decide, looking at her, that the time for that particular caution has passed. I think there is something beneath this ice shelf that is not geological in origin, that has been here for a very long time, and that is in some meaningful sense becoming more active. She nods, not surprised, not dismissive. She writes something in a small notebook. That's consistent with our current working hypothesis, she says. The weeks that follow exist in a compressed, airless state that you will later struggle to fully reconstruct in memory. A drilling team arrives, then a second team, then a crate of equipment whose manifest you are not given access to. Halley 6 becomes something it was not designed to be, a staging point for an operation with no public name and no public existence. You are given a temporary security classification, which is both an expansion of your role and a reduction of it. You now know more. You are now permitted to say less. The drilling begins at 2,400 meters depth, extending the existing borehole system deeper toward the signal's apparent origin point. The work is painstakingly slow. Antarctic ice drilling always is. The ice wants to close, the cold defeats equipment. The logistics of deep access operations at the bottom of the world are a continuous improvisation against entropy. While they drill, you continue your monitoring work. The signal continues to grow. By week 3 of the expanded operation, it is 22% stronger than baseline. By week 5, 29. The intervals remain exactly 47 seconds. The harmonic structure remains intact. Only the amplitude changes, and it changes consistently upward. Coletti briefs you on the working theories periodically, in fragments. You piece together what you can. The prevailing hypothesis among the assembled specialists is that the signal originates from a structure, a physical object or installation, situated at or near the bedrock interface, beneath approximately 3,100 meters of ice. How old it is, no one will say with certainty. But the geological context of the layer it occupies, the ice strata, the known accumulation rates for this region, places the depth of the bedrock at an age of not less than 800,000 years. 800,000 years. You sit with that number in your bunk at night, turning it over. You think about what existed 800,000 years ago. Homo erectus. No written language anywhere on Earth. No civilization, no agriculture, no metalworking. Anatomically, modern humans were still 500,000 years in the future. Whatever is down there predates us. Not by a little. by an unimaginable margin. On the 41st day after your initial discovery, the drill reaches 3,080 meters. The sensors at that depth detect a change in the ice, a density anomaly, a boundary layer that doesn't match the expected geological profile. Coletti pulls you into the monitoring room at 2 a.m. to look at the data. What you see is a cavity. Not large, estimated 12 to 15 meters across based on the acoustic returns. A space beneath the ice, above the bedrock where nothing should be. And from inside it, the signal. Now, at this depth, it is not just a low-frequency pulse in a dataset. Routed through the borehole's acoustic relay and amplified to audible range, it becomes a sound. A slow, deep, rhythmic sound. You hear it through the monitoring headphones and you hold very still for a very long time. It sounds in some way that you cannot explain technically and will not try, like something waiting. Coletti is watching your face. We're going to need to lower a camera package, she says. I know, you say. I want you to run the imaging analysis when it comes back. You take the headphones off slowly. Why me specifically? Because you found it, she says. And because you went back on day 8 when you didn't have to. That matters to the people making these decisions. You don't ask which people. You've learned not to ask questions that will give you answers you'll need to carry. The camera package goes down on day 43. You monitor the feed in real time from the surface ops room with 6 other people, all of them quiet, all of them still. The descent takes 4 hours. The borehole is narrow, the equipment fragile, the cold at depth severe enough to demand constant heater compensation in the instrument housing. At 3,074 meters, the camera enters the cavity. What it shows you is this, a surface. Dark, smooth, and geometrically regular in a way that raw geology is not. The camera's LiDAR return maps an object roughly 11 meters in its longest dimension, embedded in the ice at the cavity's base, partially encased in what appears to be ancient glacial material that has slowly accreted around it over timescales your mind won't fully process. The surface of the object, whatever it is unmarked. No visible seams, no visible damage, no obvious point of entry or function. It is simply there, where nothing should be, doing what it has apparently been doing for an incomprehensible length of time. The signal is coming from inside it. On the feed, the object's surface appears to respond fractionally to the camera package's proximity sensors, a barely measurable shift in the acoustic output, a microsecond change in pulse timing. Not a reaction to the camera, a reaction to the active sensor emissions. It notices things. You write this in your analysis without softening the language. Something down there, after 800,000 years, still notices things. The report goes to Coletti within the hour. She reads it, makes 2 calls you are not party to, and then finds you in the corridor. We're expanding the operation, she says. Your role is going to change significantly. That can mean more access, or it can mean a different kind of reassignment. You think about the sound through the headphones. The slow, deep pulse. The thing that waits and notices. More access, you say. She nods. Then you should know that, as of this morning, this project has a name. It's called Pale Fire. You're now the primary scientific liaison for the drilling team and the recovery operation. That means you report directly to me. You hold a full clearance for all operational data, and you do not communicate with anyone outside this project about anything related to this facility or its findings. Not Fenwick. Dr. Fenwick has been reassigned. He'll continue his atmospheric work at McMurdo. You absorb this. And if I'd said I wanted the other kind of reassignment, you'd be on the same flight as Fenwick, she says. But you wouldn't have said that. You went back on day 8. 3 months pass. PLE Fire grows from a field camp improvisation into something that has its own logistics chain, its own dedicated satellite bandwidth, its own rotating security personnel. The station above is still officially Halley 6, still officially a glaciological monitoring outpost. The work below is something else entirely. You learn the specific vocabulary of working at the edge of what human knowledge can contain. You learn to write reports that are technically precise about the observable while remaining agnostic about the interpretive. You learn that the people above Coletti in whatever structure she belongs to are not scientists, and they ask questions that scientists don't ask. Not what is it, but what can it do and can it be moved and who else knows. You learn to answer carefully. The signal continues to grow. 60% above baseline now. Still perfectly timed. Still harmonic. Still, as far as anyone can determine, entirely autonomous. No external input required. No power source identified. No degradation in output despite the age of whatever is producing it. On a Tuesday in what the calendar tells you is October, though October has no meaning at the bottom of the world, you are running a new frequency analysis when a second signal appears. Not from the object. From somewhere else. Different frequency, different interval. But structured. Harmonic. You sit with this for 4 minutes before you call Coletti. There's another one, you say. Pause. Where? You check the bearing calculations twice before you answer. Approximately 340 kilometers east-southeast of our position. Same depth signature. Another pause, longer. Same characteristics? Similar. Not identical. The interval is 53 seconds. You hear her breathing. You hear her not saying the thing that the data is saying. Send me the full analysis, she says. Already done. You sit in the monitoring room after the call ends and you look at the 2 signals on your screen. The 47-second pulse you've been living with for months, and the new 53-second pulse from somewhere in the ice to the east. 2 sources. 2 intervals. 2 of something that shouldn't exist once, let alone twice. You open a new mapping window and project both signals' origins. You draw a line between them. Then you sit back. The line, extended, passes through a third point, a location roughly 280 kilometers to the northwest that you have not yet surveyed with deep array sensors. You look at this for a long time. You are not going to put this in the analysis you already sent. Not because you're hiding it. Because you need to be certain before you add a geometric relationship between 3 hypothetical source points to a report that is already the most significant document you have ever written. You pull up the deployment schedule for the Eastern Array expansion. 6 weeks out. 6 weeks to find out if the pattern you're looking at is real. You save the mapping window to your local drive and close it. Outside, the Antarctic wind is doing what it always does. The bass groans. The lights hold. Below you, 3,074 meters down, something pulses at 47-second intervals. Further east, something new pulses at 53. And somewhere to the northwest, in ice that has never been surveyed at depth, there may or may not be a third point on a line that should not exist. You've been down here for 14 months now. You are no longer certain you are doing science. You're not sure what you're doing. But you open a new analysis window and you begin.